Here we go. As a quick review, number one, momentum. Momentum is an object moving, number one. Can an object be at rest? It sure could, but it would have zero as a momentum. The definition for momentum is how difficult it is to stop an object. One more time. The definition for momentum is how difficult it is to stop an object. So when an object is moving, it has momentum. Now, I just want to make sure that we're all on the same page. We can have a car driving out here, and it can be going. It's going to have momentum. You know these ducks? What if they're flying across the pond to the other spot? That can have momentum. What about an atom? It would have momentum, right? Because all atoms are moving. We can get down to the electron of an atom. Again, it has momentum. Now, don't get me wrong. An electron is extremely small, minute mass, but it still has momentum. Okay? It still has momentum. Atoms, extremely tiny, they still have momentum. So any object that has mass and has movement has momentum. P equals m times v. It is on our formula chart. I'm going to turn the page. As a quick, just again, a little bit of a review. Impulse. Impulse is pretty much the opposite of momentum. Momentum is moving, and impulse is trying to stop it from moving. Now, if impulse is the exact same number as momentum, or greater, it is going to stop it. But if impulse number is less than the momentum, it won't stop it, but it'll probably slow it down, okay? Now, impulse is J equals F times T, and the cool thing about this is that it has the same SI unit. We love this in physics, because when we have two objects or two equations with the same unit, we can set them up equal to each other, and we can find an unknown variable. And that's what we're going to do when we are with one of our labs next week. Okay, the definition for impulse is the change in momentum, meaning we can speed it up or slow it down. We can speed it up or slow it down. I understand it's kind of the opposite to slow it down, but can't you push something with a force and make it go faster? You can also speed it up if need be. And then we got to this impulse equals momentum equation, or J equals P. We can rearrange it, and we can say J equals mv, or we can say P equals ft, because they're exactly the same SI unit, so we set them up equal to each other. Alrighty? Then we got into this crumple zone. And yes, cars are made nowadays to where they start to have all of this damage. It looks like a bad car wreck. It may not have been that bad, but there's some major damage, your hood, your fender, your bumper, all of that happened. And why is that? Because when an object's moving and it crumples up into a small piece, that increases the time for it to come to a complete stop. And if I can increase the time from coming to a complete stop, then I can decrease the amount of force on an object. Now, don't get me wrong, we also try to wear seat belts. We have those airbags. Sometimes we have side airbags. The problem here is that a person could be in a car wreck. The police officers come. It looks a little bad. Maybe it doesn't even look that bad. But the first question they're going to ask you, are you okay? If you look maybe a little beat up or maybe a little scratched up, they might even tell you, I think it would be good for you to go ahead and just go to the emergency room. And you might be like, hey, I'm okay. I'm walking around. You may be okay for that moment, but who's to say when you're driving, your organs are also traveling at the same velocity that that car was moving? You don't have seat belts around your stomach, your spleen, your heart, your intestines. They also experience that amount of force. And so there could be some internal injury. So sometimes that's why they suggest, well, you know what? Just in case, go ahead and go to the hospital because of momentum. The amount of momentum that your car experiences is the same amount of momentum that your body experiences, that impulse, right? Then we started talking about how do we do this, or how do we slow that down or ease it? Well, that's by increasing the amount of time so we can decrease the amount of force, all right? And then we ended up over here. The last class we looked at those new football helmets, which are starting to come out, and people even in the NFL are wearing them because of that padding to help decrease the amount of force that's going to occur with their brain, right? How do we do that? By increasing the stop time to decrease the amount of force. Now, the next part over here is called follow through. Follow through. So some of us, we have had, I don't know, maybe played baseball, softball, what other sports? Tennis. Oh, pickleball. Pickleball is a new, major big sport nowadays, right? Golf. Anybody who plays golf? Somebody, a coach, a parent sitting in the stands, maybe screaming at you. Follow through when you're swinging with your bat. Follow through with your racket. Follow through with your golf club. Okay? So let's go ahead and let's try to see what we're talking about over here. Because believe it or not, I think your coach and your parents are trying to explain physics to you, and I'm just not sure if they understood the whole process. So here's my example I used earlier today. I use it quite often. All right, Houston Astros. They've got a couple of, meh players. But either way, I'm going to go ahead and use Jose Altuve as an example. So for those of us who are familiar, Jose Altuve, he's kind of a short guy. He may not like my lecture if he heard it. But he's a short guy, 5 foot.
4.
With shoes.
No, he's 5'6".
That's with shoes.
No.
Yeah, he's got those thick Nike ones. You know what I'm talking about? Those Nikes are like those platform almost, kind of like, you know what I mean? He's got thick shoes on, let's be honest. 5'6", with thick shoes, and he's probably including his hair. Okay, let's be honest. Okay, bless his heart. I know he makes a lot of money. He's gonna have short kids. Okay, either way, that's all right. That's all right. He's a small guy. Next question. When Jose Altuve or any other baseball player, softball player, tennis player gets up there, do they just go up there just to play like, meh? Or do you kind of think or believe in your gut or in your brain that they're probably out there to win? Just saying. Are they there to win? I know I expect my kids to go up there, and when you're getting up there to play, you better be up there to win. Whatever it takes. You go to school, you better be there to win and make good grades. I don't care if you're tying your shoes, it better be a W on the best shoe tying you do in your life. Okay? Everything in life needs to be at the utmost best. You give it your all. Then why are you doing like that? You don't give it your all. So I'm going to assume that Jose Altuve, the time that he got up there to bat, any time that he gets up there to bat, he wants to give it his all. Do you believe that he gets up there and he's like, meh, I'll just, I'll swing and, we'll just, meh. But the next time, I'm really going to try harder. No, he probably tries hard every single time. Bless his heart, can he grow any taller before next season, 2026 preseason? No, he ain't going to grow any taller, right? He's already full height. Wait a minute. Could he or any other baseball player bulk up significantly bigger? Way bigger. A little bit bigger, but significantly bigger? I mean, I've seen Carlos over here for 2 years. I haven't seen a significant bulking yet. Carlos goes to the gym. That's why I try to go during the day. Okay, well, I'm going to go overnight at 2 a.m., so I don't have to see you. Either way, Jose Altuve and any other baseball player, they can bulk up a little bit, but is it going to be such a big difference? Dang, look at him. No, it's the same every single time. Okay, what about one baseball game? Let's say he goes through the lineup 3 times. Did he get taller in between it? No. Did he bulk up in between it?
Maybe.
No. Did he get stronger in between that third lineup that he came up? No. But what he can do, and any other baseball or golf player can do, is they can follow through. So let's go ahead and fill that in. Here he is. Right? Here's his bat. Okay? And so what he can do is he can follow through, and when he follows through with this bat, swing all the way through, he can increase the amount of time that the bat is in contact with the ball. That's the purpose of follow through. I don't know if the Houston Astros has an actual physics teacher in the dugout, but I have no problem being the volunteer to be the dugout teacher to explain physics of why I expect you to follow through. So when you're out there swinging and the ball, you make contact with the ball, if you follow through, that is going to increase the amount of time that the bat and ball are in contact with each other. If you can do that, do we all recall our equation of momentum impulse? I'm going to write it in just in case if you forgot it. mv equals ft. If you can change this, check, by following through, this also includes soccer players, like I said, tennis players. If you can increase the amount of contact time, and if you can change this portion of the equation, it will cause, aren't these two equations equal to each other? If you change this side, you are going to cause a change over here. That's why you follow through. Because now, when you increase the amount of time because you're following through, you're going to change something over here. What am I going to change on this side? What do I cause a change of? Can I cause a change of the mass? No. The ball mass is not going to change. The mass stays the same. So which variable is going to get changed? The velocity. The velocity is going to get changed. And so when this velocity gets changed, why? Because those two equations are mathematically equal to each other. When you change this side, you cause this side to change. Now I'm going to have out of the park home run hits because you follow through, which you cause the change, right? It's not the force. It's not the force. When you came up to bat, you didn't bulk up bigger and you're stronger. No, you're the same person that you are. It's not the force. But when I cause this side of the equation to change, now I'm going to force this side to change, which is going to increase. If this increased, it's going to increase the velocity. And as a reminder, velocity equals, do we remember that equation? We did it so much last semester, d over t. And if I cause this velocity to change, if I cause this side of the equation to change, I'm going to cause the other side of the equation to change, which is this. Now, this ball, out of the park home runs, distance. That is the physics of how we can cause out of the park home runs. Now, Carlos, if this baseball season you don't take what I just taught you right now and do more out of the, how many did you have last year? 2. Okay, so you should have at least 8 this season.
8?
8. How are you going to do it? Carlos plays baseball, for those of you who don't know. Hitchcock baseball team. How are you going to do it?
Follow through.
Follow through. Why follow through? Because you're changing what side of the equation?
The right side.
The right side, which is the T. Not the force. Cartwheel didn't bulk up, no matter how many protein bars he
No,
ate.
I was thinking, I was gonna say
Oh.
the T.
The T. And when you cause one side of the equation, the T, to change, it causes not the mass, but the velocity to change. And the velocity of the ball is going to change. When I change the velocity on V equals D times T, it causes the other side. It's a yo-yo effect. It's a yo-yo effect. And so when I cause one side to change, mathematically the other side has to change, which is the distance. Now you're having out of the park home run hits. Okay? That's the way to do it. Now, for those of you, let's continue. You have your notes out. If not, you know I traditionally scan the notes, and I'll do that today, and I'll put them on D2L just in case if you miss something. And I'm videoing the lectures, so I'll start posting those today, just in case if you want to rehear something. But let's scratch this out. It's just fill in the blank. It's not that important. This is what we need to get to. Conservation of momentum. We're about to get to our last major, and this is going to be a little tricky for some students, okay? This is our last equation, and you know I always start with the easy equations first, and then I get to the hard ones later. We're about to get to this one. It says here that momentum is conserved during a collision, which means that the amount of momentum in a closed system before a collision is going to equal the amount of momentum in a closed system after the collision. Remember, we talked about open systems, closed systems last semester, and right here mathematically, we are going to assume that all of our systems are closed systems. That way our numbers are equal to each other. Well, true story, we live in an open system. Remember, that value didn't disappear. It just got transformed into another formation or another type that we missed. We didn't get to capture that value. So we are going to assume this school year that we are always going to be in a closed system. But wait a minute. If mathematically you get two numbers that are not equal to each other, it's okay, true story, because that means it must be an open system, right? But we like our numbers to be equal here at this level of physics. It says that an open system is a situation when things can be exchanged with the environment. And this is like true story, real life. Unfortunately, oh man, I missed that. Where'd it happen? There was friction, there was heat, and so my numbers are not equal. It says that a closed system is where nothing is exchanged with the environment, so everything inside is conserved. Conserved. A closed system would be like it says here, if for an example, the U.S. stopped doing business with other countries and they made all of their own products. That would be, you would not be wearing Nikes anymore. Nikes are not made in the U.S. Everybody be wearing Hey Dudes. Those are made in the U.S. No, I don't think they're not. But they're not made, they're made somewhere else. Either way, that would be the example. When you're ready, turn the page. Because we're about to get into the three types of collisions, and then we're going to get into the math of these three types. There are truly 4 different types of collisions, but we are only going to learn about 3 of them, okay? Here is collision number 1. It's called an elastic collision. Collision number 2 is an inelastic collision. And collision number 3, explosion. Okay? Collision number 1, collision number 2, collision number 3. I'm going to need, here, I'm going to use a yellow marker and a pen. All right, so collision number 1, which is called an elastic collision. Why am I talking about these 3 collisions? You need to be able to read the math problem that we're going to start having and decide which type of collision is occurring. And then that is going to determine how you are going to manipulate the equation. Okay? So let's go ahead and take a look. Elastic collision, it says here that these are collision where things hit each other and then they're going to bounce off. You start off with 2 objects and you end up with 2 objects. They bounce off. For an example, playing pool. You hit one ball, it bounces and hits the other balls. They don't stick together, they bounce away. Here's the thing, it doesn't have to just be 2. It can be 3, it could be 4, it could be 7 objects. It doesn't matter. Bowling. You get the bowling ball, you roll it, hit the bowling pins, they all bounce, but they don't stick to each other. Again, you can make a decision on how many objects are going on. And when you read the equations, you need to determine how many objects. So my example over here is object number 1 plus object number 2 collide, and then object number 1 bounces off and does not stick to object number 2. There we go. Object 1, object 2. If I had a third one, I would get a third color and I would do a plus sign and I would do 3 on the right and 3 on the left. If I had 4 objects, 4 on the right and 4 on the left. All right. The next one, inelastic collision. An inelastic collision is where things are going to hit each other, but when they hit each other, they actually stick together. It says here that you start with, let's just say for an example, 2 objects. Again, it could be 3, 4, 5, or 6. And you end with 1 object because they all stuck together. Here's my example. It's a good example. There's a big fish. There's a little fish. The big fish ate the little fish. Now we got 1 fish. Makes sense. You had your breakfast this morning, your Pop-Tart, your food. It was you and the food. You ate the food. Now you and the food became 1 new object. Makes sense. Now when you go and pee and go to the bathroom, now you are 2 objects again. I know, right? Weird. Okay, no worries. Here's another example. Astronaut A and astronaut B are in space. They're floating and they collided and now they're stuck together. Makes sense? Easy cheesy? Let's go ahead and do this one. Object number 1 plus object number 2 are going to collide, and now object number 1 and 2 are stuck together. Not bad. The third one that we are going to talk about is explosion. So when it comes to explosion, it says here, explosion, these are events where 1 object breaks into multiple parts. So you start with 1 and you end with 2 or more objects. Explosion. Ooh, Whew, I had an explosion. Boom. If you ate your breakfast this morning, you weren't feeling too good. Boop, you threw it up. That was an explosion. There you go. This bird caught a fish, and when he was flying, he lost the fish. It came out of his mouth. Explosion. Next example, we've got a skateboarder on a skateboard. There, he's riding, happy, A-okay, hits a rock or does something, falls off, explosion. Makes sense? But it could have, what if he broke the skateboard? Then it became him and two parts of the skateboard. That would be three parts. Okay? So you can have more, two or more things after it explodes. So let's go ahead and do this example. Let's see what it looks like. Object number 1 explodes. Oh, wait a minute. Remember, object number 1 could be more than one thing. What if this bird had two fishes in its mouth? But I'm just going to do one fish. The bird and the fish in his mouth is together. Explosion occurred. Now I have the bird plus the fish, which are separate. Now, first thing is I want to talk about, back at elastic. I have circle number 1 and circle number 2 collide, do not stick together, and look at circle 1 and circle 2. They're about the same size. Let's look at this one. Circle number 1 plus circle number 2 collide, stick together in elastic collision, and what happened? It got bigger. Okay, what happened was the two masses combined into one new mass. The law of conservation of mass says that my mass is conserved and I can't just poof, lose any mass. Over here, my explosion was one quote unquote big object. It exploded into multiple smaller parts. But if I got all of these parts and added them together, it would still equal the mass of the original object. Okay? All righty. So I'm going to do this equation, and this right here is one equation. I'm going to do it into broken up parts though, okay? This will not be on next week's Tuesday's quiz. It will be on quiz number 2, but I just want to show us, and then we're going to turn and do another page and a little bit more, and then we're done for our notes for today, okay? So here we go. For our collision equation, we're going to do it into two different parts. We are going to do right here the before, and this is going to be the after collision. So we've got two soccer balls. It says both soccer balls have the same exact mass. So that mass is for soccer ball 1 and soccer ball 2. It says they are moving east. Remember, momentum is a vector quantity, but I'm not going to be of any concern, and I'm not going to have y'all stress on that. Soccer ball A is moving faster than soccer ball B. Soccer ball A has a velocity of, this is soccer ball A, this is soccer ball B. It has a velocity of 0.84 meters per second. It says over here, soccer ball B, who is definitely moving slower than soccer ball A, has a velocity of 0.04 meters per second. Calculate the total, what's the word total mean? Add the total momentum of both soccer balls. Well, my equation for momentum is m times v, or for soccer ball A, mass of 0.47 multiply by 0.84 equals the momentum, kilograms times meters per second. Soccer ball B. Soccer ball B is going to have the same equation, P equals M times V. It so happens to have the same mass, which is 0.47, but its velocity is actually smaller than soccer ball A, 0.04. find its momentum, and then the next question below it says, hey, what is the total net momentum? That word net, just like we talked about last semester, means to add. So to find the total net momentum would mean to add both momentums together. So let's do that. And when we do that, we're going to find the total net momentum before the collision. So the total net momentum before the collision is 0.4136 kilograms times meters per second. Now this is the before. Remember, I labeled this over here, before the collision. Now the law of conservation of momentum states that my momentum before the collision should equal the momentum after the collision. Okay, so let's look at this. So it says, okay, now soccer ball A actually catches up with soccer ball B. Because why? Remember over here was moving faster. When this occurs, the two balls collide. They don't stick together. When this collision occurs, soccer ball A came to a stop. So soccer balls A's and soccer ball B. Its velocity came to a stop, so hopefully you recognize that's 0 meters per second. Soccer ball B actually accelerated or got faster, and so for its velocity, it became 0.88 meters per second. So they're asking us, well, let's go ahead and let's find the after or the final momentum. Again, same equation, m times v. The mass, what's my mass number now? It's the same, 0.47. Mass never changes, I agree. The velocity became 0, and so soccer ball A's velocity after the collision is 0 kilometers times meters per second. On soccer ball B, its equation, which is m times v, and again, mass never changed, but its velocity changed because it got, what happened? The velocity of soccer ball A gave its quote-unquote energy, its velocity to soccer ball B. Now B is moving faster. Why? Due to the law of conservation of momentum. That's why. And if you actually multiply this out yourself, you would see what its new velocity, its new momentum. This was its momentum before, this is its momentum after. You can see the momentum before is different from the momentum after for both soccer ball A and B. It says here, well, what is the net momentum after the collision? There you go. It should be exactly the same thing because 0 plus 0.4136 equals 0.4136. Kilograms times meters per second. Exactly. You can see that it is the same because of the law of conservation of momentum. They should be the same. What type of system? Closed system. Okay? So it says here, how does the momentum before the collision compare to the momentum after the collision? They're the same. But don't forget though, they're the same due to the law of conservation of momentum. That's why they're the same. And then the next question here says, well, what type of collision occurred? Is it elastic, inelastic, or explosion? I agree. elastic collision because they don't stick together. They don't stick together, so it's an elastic collision. Easy cheesy? We're almost done. Tomorrow we should be done with our notes, so that way we can get ready for our labs. Turning the page. So being able to practice, read the word problem, and that is going to determine, because guess what? There's only one equation to use for all three different types of collisions. You need to read the problem and in your mind know which type of collision is occurring so you can manipulate. Remember last semester how we had the Power Ranger morphed kinematic equations? Well, we're going to have this Power Ranger morphed version for momentum, and you are going to have to manipulate it to the situation that's occurring. Number one, a piece of gum hits a window. Well, if they told me it's a piece of gum, they're trying to infer that it got stuck to it because it's a piece of gum in elastic collision. The tennis ball hits a wall. Elastic, because it doesn't stick to the wall. A car crumples, oh, wait a minute, listen to this, into. The word into is inferring that it stuck into each other. Inelastic. A paintball breaks into multiple pieces. Explosion. A bumper car hits another bumper car. Elastic. And Morpheus and Neo from the Matrix run into each other and they catch each other and collide and catch each other in midair in elastic collision. I'm going to have to change that example. Not a lot of people have seen the Matrix. All righty, so I'm going to skip this portion. We're going to finish this part and then we are going to write the equation down. And that's it for the day, okay? And then we'll finish our notes tomorrow, be done, and get ready for our projects and our labs, which is great. It says here, the conservation of momentum of collision. Remember that momentum before a collision is always going to equal the momentum after, but in a closed system. That means that P before needs to equal P after, or P initial needs to equal P final. It says here, to find the momentum before, we must find the momentum of each piece before the collision and add them together. Meaning that the P before equals, and this is only if I have two objects. If I have three, it would be longer. I'm going to call this the mass of object 1 times the velocity of object 1 plus the mass of object 2 times the velocity of object 2. And that's only if I have two objects. If I had three objects, I would say plus the mass of object 3 times the velocity of object 3. And then it says here, to find the momentum after, we must find the momentum of each piece after this collision occurred and then add them all together. So the P after, or the P final, equals the mass of object 1 times the velocity of object 1 plus the mass of object 2 times the velocity of object 2. Again, this is only if this is two objects. And if you look at this, this is broken into two parts. This is before the collision, and this line is after the collision. But what does it say up here? The before equals the after. So now let's write this all as one equation, because this is one part and this is one part. These two parts need to be added together to equal one equation. So we're going to turn the page, and I'm going to write it as one full equation for you. This one equation, which is our last equation, is M1b, the mass of object 1 before the collision, times the velocity of object 1 before the collision, plus the mass of object 2 before the collision, times the velocity of object 2 before the collision. Again, remember, this is only if two objects are involved. If it's three, I promise you on the test, it's going to be like 3 or 4 objects. So you would continue to add and grow this equation bigger, as big as you need it, equals the mass of object 1 after the collision times the velocity of object 1 after the collision, plus the mass of object 2 after the collision times the velocity of object 2 after the collision. Okay? That is one equation. Here it is typed up for you. Here it is when we write it. We are going to come over here and we are going to, on tomorrow, Power Ranger morph it to the type of collision, elastic, inelastic, or explosion. That's what our job is tomorrow. We're going to work those math problems. We should be done with our notes. You have an awesome